Hi everyone, welcome to my YouTube channel. So I will be talking to us about something that I think many people have requested that I should do this video. Sorry, it's been taking me time to be able to get it done. It's because of a number of commitments I've got. So we are going to be looking at Levey-Jennings chart, and we're going to link that to the rules of Westgard rule. Okay. Now, hopefully that can help us to be able to have better understanding of why this has to be one of the common questions they ask in biomedical science. So before we continue, my name is Dr. Emmanuel Obodo. Obviously, as you can see, I'm a biomedical scientist, and I'm also a lecturer in biomedical science here in the United Kingdom. So yeah, let's look at Levey-Jennings charts or Levey-Jennings graph, depending on what you want to call it. And we're going to try to connect that with Westgard rules. Okay, right, let's get into that. Now what we are going to be looking at today is, first of all, look at the Levey-Jennings chart. What exactly is Levey-Jennings chart or Levey-Jennings graph? Then from there we can now link it up to see what is Westgard rule, and how do we combine these rules with Levey-Jennings chart. And I'll try where possible to provide a kind of topic. I'll try to provide application in biomedical context, like to make it more real. Hopefully that can help us to understand what this is talking about. And obviously we're going to look at series of interpretation of Westgard rules, and of course see the is important for biomedical scientists. Okay, and then look at some few practical examples. So these are the things I hope to cover by the end of this presentation. Right, the learning outcome of this is that by the end of this session, I hope we should be able to understand the principle of Levey-Jennings chart. We should be able to understand the principle of Westgard rule. Then we should be able to understand practical interpretation of Levey-Jennings chart / Westgard rule. Okay. Now, what exactly is Levey-Jennings chart or Levey-Jennings graph, depending on how you look at it? What I want you to know is that, obviously, I'm sure this happens to be one of the common things that I'm sure that many of us know. So in the laboratory, obviously, for us to be able to certify or come to conclusion that the laboratory analysis, that the test we've run, that is consistent as a true result of the patient or true patient result, we've got to have a way of determining that all the processes involved in carrying out that test meet up with the standard. There is no fault, that the processes are reliable, reproducible, as the case may be. Now, let me just say this as a little background. So when we talk about these processes, it's not just entirely the analyzer. Analyzer is just one part of the processes that you have to ensure that your system is working correctly. So when you look at your standard operating procedure, the processes involved in carrying out the test, including the sample preparation, how the test should be run, and all of that. Okay, obviously the analyzer, when you look at maybe things like the quality control chart, when you look at something like calibration and all of that, these whole things contribute significantly on how we are able to determine if the process is up to standard or have missed standard. Okay, is one of the ways we can confirm that the processes has meet standard or the processes have meet standard. Okay, or met standard actually. So now let's look at it. What Levey-Jennings chart means. First of all, you have to know that it's a graph. And in this graph, what we do in this graph is that we use this graph to kind of determine or monitor the performance of the analytical method over time. For example, when you are doing the quality control or whatever thing you are doing, so over time, periodically, maybe after 1 week or 2 weeks or 2 days, as the case may be, so over time we can check using the Levey-Jennings graph and see how that process is performing, how it gives us an indication of whether the processes are still maintaining standard or is there possibility that there are some errors that could have associated with the processes that may invariably impact on the overall patient result. I hope we are getting what I'm saying. So this is why when you look at this Levey-Jennings chart or Levey-Jennings graph, it can show you, like you can see here, the plot. We plot it daily, and this daily plot can help us to see the trend of the quality control. Okay, and of course it can help us to see the shift, whether the quality control result, whether is it at the mean, is it at the lower mean, is it at the upper mean. Okay, which we are going to look more. But when we find out that whether it is upper mean or lower mean, depending on the way it shows, sometimes the way it shows could suggest that there are some kind of errors, okay, that may have associated with that process or with that the processes involved, that time. Okay. Now, and this is why we have to determine each of these processes, because it will help us to know on time how to tackle it and make sure that we are able to detect it on time. This is why this happened to be one of the most common questions they ask in biomedical scientist job interview. Why? Because without the understanding of the Levey-Jennings chart and Westgard rule, you can't be able to determine if the results you are processing or you have given out, whether they are correct or not. And that is one of the primary roles of a biomedical scientist. So that's why it's important. Anyway, why did I say this? So the outcome of the result we see on this chart could tell us whether there is error, maybe something like random error or system error. So, I've taught us before on systematic error and random error. So this Levey-Jennings chart can give us a clue whether what we're dealing with in terms of error where possible or where it has occurred, whether the errors are, whether the kind of errors we're seeing, whether it is random error or systematic error. Okay, right. So Levey-Jennings chart is a chart or a graph that helps us to monitor the performance of analytical method over time, and that plot will help us to see the trend of the quality control, see the shift, okay, of each of the points of the quality control, and that can also help us to detect where possible whether there is a presence of either random or systematic error. I think I'm just going to show us example. So this is just example of Levey-Jennings chart. Okay, so these are the key components. Remember, like your normal graph. Let me see if I can draw. Okay, just permit me. Let me see if I can draw. So let me try to draw. Remember that we can plot a graph like this, and obviously this is your I don't know if I can write well, like, you know what I mean, this is your y-axis and this is your this is your x-axis. Okay, so now you plot a graph. So this somehow supposed to be the mean, and now that the mean is like this. So when it is upper, that is upper standard deviation. When it is lower, that is lower standard deviation. So, but this is the mean. Okay, so what this is trying to show us is that when we say Levey-Jennings chart, the east component is this y-axis. Okay, let me see if I can change it to this. Okay, so is this y-axis and x-axis. Okay, so that's the main component. Now the mean is the average value of the horizontal, which is what I've just shown you. So this is the mean. The line here is the mean. Now the standard deviation is whether it is above or below as the case. So when the standard deviation, the values up here is the upper standard deviation, while the value down here is the lower standard deviation. Does that make sense? Now when we are looking at, when we perform a quality control, what we are trying to find out, where exactly is the point of our result? Is it at the mean, or is it at the lower standard deviation or upper standard deviation? What we are saying then is that the position, the location of the point of that very quality control, that time can give us strong indication whether the processes are performing as expected or whether there's a possibility of errors, like maybe systematic or random error, or as the case may be. So just to give you an example, so you can see this is a mean. So now, even though it is the upper mean here, it's not exactly at the mean, but you can see it's okay, and it's still okay here. So while we have run this test now, so at this point we can say that the quality control has passed. At this point it's also passed, but here look at it's red because why? It has, this is the mean, this is actually what we expect, but due to the variation which I will show us as we progress, that is why sometimes it can go up and down and all of that. But once the point of the quality control goes above these two standard deviations, as you can see here, that is not very good, and what it means that we need to investigate it. And there's a number of reasons that could lead to this. It does not mean that the process used to run the test may not be wrong. However, the approach used in running the test may be wrong. What I mean is that the SOP, the analyzer may not be the problem. The step-by-step that you take may not be the problem. Maybe there can be something like, human error. For example, imagine not mixing the sample very well can give this point here. So that's why once you get it, it does not necessarily mean that, okay, something is wrong. What it means that you may need to retrace your step and find out what is wrong and see how you can be able to correct where possible and repeat it. Perhaps most times it will come back to what it's supposed to be. But obviously, if it continues, something then is definitely wrong. So this is just example, of the Levey-Jennings chart. Okay. Now remember, when we're looking at this, we've not started looking at them. Some of the things I've already explained suggest Westgard rule, but let's still ignore that for now and concentrate on the Levey-Jennings chart. So what Levey-Jennings chart will show you is just the graph, as you can see here, or as I've tried to draw here. That's what it can show you. It will show you the graph, show you where the result, the point of the analysis, where exactly it is. Now, wherever you find it can help you to think, is everything okay or is something wrong? Then you find a way to investigate it if you think it's wrong. All right. So now, why do we need to look at the Levey-Jennings chart? Why is Levey-Jennings chart important? In fact, this is also synonymous with Westgard rule, okay? But why is it important? It's important because it helps a biomedical scientist to be able to detect any form of analytical errors early. And not just to detect the analytical error, it helps us to detect it on time. It's important to detect it on time. In fact, if you don't detect this on time, this is one of the reasons why people may fail. I mean, the hospital or the laboratory may fail their external quality assessment, like NEQAS, as the case may be, okay? So it's important, one, there is error, and it seems like it's persistent. We need to investigate it, and detecting it on time will help in the investigation, and that can help to stop any potential negative impact that may have on the patient result or the overall performance of that laboratory. Now, and of course, another purpose is that because if it helps us to detect the error, it then means that it can help us to ensure the patient result, that the patient results we are producing, they are accurate and reliable. What that means is that by the time the result, the Levey-Jennings chart suggests to us that everything is okay, it gives us confidence that the patient results we are releasing, they are accurate and they are reliable. So these are the two main purposes of the Levey-Jennings chart. One, to detect the analytical errors where possible, and of course help to give us confidence that the results we've generated, they are accurate, or they may not be accurate. Remember, so depending on how it goes. So Levey-Jennings chart tells you what to do, either to act if you suspect that the result you are producing is wrong, or to relax and say, okay, everything is fine based on what you've gotten. I think I should we'll look at this more. So the way I want you to look at this, imagine this is just example, and I think because these questions, even though it's common both in hematology, microbiology, immunology, and all of that, but most times these questions significantly comes out in biochemistry, and that is why I chose to use glucose as example. So imagine that we have a glucose control. Remember what I draw for us. Maybe I should try that again. Let's try that again. So I drew this for us, okay, and I said that this is the mean, okay. So imagine that this glucose, that the mean of this glucose here, that means here is 100, okay. That means here is, I don't know if I can write very well, but I hope you understand what I mean, okay. So here is 100. So because this is 100, that is the mean. That is actually what you want. But what then happens is that we can do a calibration, and that calibration can give us a standard deviation of 5. So the mean, the actual result of the patient, the mean of that result of the patient or the quality control is 100 milligram per DL of the glucose. But the standard deviation of the calibration is about 5 milligram per DL. What it means is this: when we run the quality control and it gives us exactly 100 or maybe 100.01 or 02, you are likely to see it at the mean here. Okay? But if you run a quality control that gives you something like maybe a little bit more, let's say you have 5, extra 5, like 105, for example, let me use it. So when we say that is a +1 standard deviation, what it means is that you have, remember that the standard deviation is 5, the mean is this. So each of these 5, each addition of 5 on this 100 is 1, whether it is on the positive side or on the negative side. Let me explain what I mean. So it means that instead of 100, if we have 95, is going to be minus 1 SD. Okay? Remember that SD is 5. 1 SD is 5. So when we have, and the mean is 100, so when we have 100, which is the mean, and 1 SD is 5, we put 5. That addition of 5 will make it 1 SD, because 1 SD is 5. Now again, subtraction of 5 will make it that mean that it has lost 1 SD. That will be minus 1S. Does that make sense? Okay. So I'm saying that to say that. So when we say 1S, it means that there is 1 addition of the standard deviation. That's just what I'm saying. That. So just look at this as an example. The mean is 100. Okay. The standard deviation is 5. So once you add that 1 standard deviation to the mean, that is 1S. Once you subtract that 1 standard deviation from the mean, that is minus 1S. I hope that makes sense. Okay. Now, when we say 2, when you say plus 2 SD, what it means? It means that this 1 SD, which is 5, if we add another 1 SD, which is another 5, that will become 2 SD. Do you understand? So when we say the 2 SD plus this 100, okay, remember 1 SD is 5, 2 SD will be 10. So 10 plus this mean, which is 100, that becomes 2 SD plus 2 SD, which will now become 110. Do you understand? Okay. Now remember, if we also minus 10, that means that it will become minus 2 SD. Remember that in the Levey-Jennings chart, up is positive, down is negative. Okay, and it goes on. Obviously, if we have plus 3 SD, keep seeing that this SD is 5 times 3. Okay, 3 of it will be what? 15. So that will give you 15 plus 100. That becomes 115. So this becomes plus 3 SD. So that's just the principle in which that works. I'm going to show us more practical example. I'm trying to take my time to explain this more. So now this plot, when we plot it over time, with time, then this can now help us to see whether the result we are seeing, are we supposed to accept it? Are we supposed to reject it? So when we accept it, some of the accept can be warning. Okay, when we accept it, fair enough. When we reject it, that means there is something we must have seen, and that thing we must have seen is the reason why we are rejecting it. And that rejection means that there may be need for what? Investigation. Now, as we progress, there is something I want you to think. I want you to keep in mind as we progress. This is 100. So the more we add this SD, the more is far from the mean. The more the SD, the more is far. The more we remove the SD, the more is far. So when you look at the difference between 100 and 105 here, it's just 5. And that is because the SD is 5. If you look at the difference between 100 here and 110 here, that is 10. Okay, why? Because 1 SD is 5. So that means it's addition of 2 SD. But again, here is addition of what? 3 SD. So the more the SD is added, the more the result is far from the mean that is actually what is supposed to be. Do you understand? And that is why once it is far from the mean, we start suspecting, wow, what is the problem? We know that it can be far from the mean, but the degree, the level at which it's far from the mean suggests a number of things that required investigation. I hope this is making sense, right? Okay. Now, let's start seeing the Westgard rule. Don't forget what I've told us about Levey-Jennings chart. The end point of that had already touched a little bit about Westgard rule. So for us to be able to interpret Levey-Jennings chart, we must understand Westgard rules. Okay, so Westgard rules help us to be able to interpret what is going on the chart, on the Levey-Jennings chart or graph. Do you understand me? Okay, so that means in Westgard rule we use it as a criteria, is a principal criteria. The what we look at, okay, is a guidance that we follow to be able to, interpret what that goes on the Levey-Jennings chart. So Westgard rules are just rules, the guidelines or the criteria used together with the Levey-Jennings chart or Levey-Jennings graph to be able to interpret the quality control sample. Do you understand me? Or data. Do you get the point? So I want you to know that when you say that the quality control quality control has passed or failed, what that determines pass or fail for you is the Westgard rule. So you use Westgard rule to make a decision of what is going on, but the chart itself will show you what the point of the result you are looking at. Okay, to just show you the point of the quality control, but the Westgard rule is what that forms your decision. But that guidance or criteria that help you to form the decision, which is the Westgard rule, cannot work on its own or independent of the chart or the graph. So the graph or the Levey-Jennings chart graph is a presentation of the result, while the Westgard rules are the criteria or guidance that help to inform you if you should accept the result or reject the result. I hope that makes sense. Again, the purpose of this is to help the biomedical scientists to, one, either decide, am I going to accept the result, am I going to reject the result, or will I investigate the test and run it again? Okay, sometimes it can be warning. So if you think it's warning, then you can investigate, rerun the test again, and then it may pass. But again, so there are possible reasons that it can help the biomedical scientists either to reject the result or accept the result or investigate the result. Okay, and that investigation perhaps might lead to either rerunning the test. I think that makes sense. Okay, all right. So now, since we've understood it to this point, I've already explained 1, 2S or 3, whatever thing I've already explained this already. So now, one there, okay, is telling you, the one here is trying to tell you, for example, let me put it this way. So when you say 1, 2S rule, it says a single point exceeds 2 standard deviation. So the 2 you are talking about here is this 2. The S is the standard deviation. Okay. Now, so but the 1 is the number of occurrence. Let me use that word. Is a number of occurrence. So when you run a quality control, remember what I showed you before. So if the quality control, the first time you run it, are you getting me? Which is a single point. Okay. That single point, as you've run it, that single point when you've run it, if exceed 2 standard deviation, that is 1, 2S rule. Okay, let me try this again. So the 2 is a standard deviation. Remember I told us about once you have a mean, you have calibrated standard deviation. Okay, so once there is one addition of that calibrated standard deviation, as I showed you on the previous slide, that becomes 1 SD. If it is plus 2 of that standard deviation, that becomes 2 SD. What do I say? That if you run a quality control rather, and the first point, that single point, if exceed 2, this 2 now is a standard deviation, the number of the standard deviation. So if it exceeds 2 standard deviation, that single point, which is 1, okay, exceeds 2 standard deviation, that is a warning sign. So that means when you say 1, 2S, 1 means that first occurrence or single point, okay? 2 means the standard deviation, of course, S, okay? Standard kind of, okay? Or standard deviation, okay? So 1, 2S standard deviation. So a single point exceeds plus or minus 2, by the way, standard deviation. Like I've explained to you before. Remember I said If you also minus that calibrated standard deviation, it will go down. That means on the lower side. Remember what I told you about the mean of the glucose is 100 milligram per DL. So, and the standard deviation is 5, for example. So if we say 105, that means is addition of 1 standard deviation, because the standard deviation is 5. But if you say 100 minus 5, that becomes 95. So if your result, the quality control give you 95, that will become minus 1 SD, because 1 SD is 5, as I've shown you previously. Okay, so I think that makes sense. So 1,2 SD rule means 1, a single point. The 2 now is that it is this standard deviation, it is exceeding 2 standard deviation. So there is plus and another plus of standard deviation, or there is minus and another minus of standard deviation. Okay, so you have a standard deviation that has increased by 2, or you have a standard deviation that has minus by 2. Okay, I hope that makes sense. So that becomes warning, and in this kind of warning, obviously you need to investigate and repeat it again where possible. Okay, now when you say, I think I spend time to explain that there, because I believe that can help us as we progress. So when you say 13S standard deviation, now if 2 is a 2 standard deviation, 3 then become 3 standard deviation. Remember, plus or minus means plus standard deviation, minus means minus standard deviation, like I've showed us previously. 1 is a number of occurrence. So again, we have a single point exceed these 3 standard deviation, whether plus or minus, obviously that becomes rejection. Okay, now when you have 2 and you have 2, now remember this is 2, don't forget what I told you about 1. 1 is a number of occurrence. So if 2 now is 2, that means it occurred twice. It's no longer a single point. So you've run the quality control, you've seen the result, then you run it again. Are you getting me? That's become the second point. So once you are looking at the first point, the second point, so this is a 2 consecutive points. I've done the QC the first time. What I'm seeing, I don't like it, and I repeat it again. So that second repeat is a second time. I hope that makes sense. Obviously, if you do the third one, that's the third time, and it goes like that. So these 2 suggest 2 consecutive points. Okay, so now I've told you that these 2, now the middle one here, remember what I told you here, 1 here is a single. So the middle one here that says 2S is talking about 2 standard deviation. Okay, so what it then mean that these 2 consecutive points exceed 2 standard deviation. So if you look at it, the difference between this and this is on the number of occurrence, just to make it easier. The difference between the 1 here, 1,2S, and 2,2S is the fact that this one is a single point, and that is why it's a warning. That is why it's a warning. And from the warning, if you repeat this again and it still gives you the same result, it becomes 2,2S. And that 2,2S at this point, you have to be very careful. Most times it's likely to be what? A systematic error. And sometimes this can be, of course, when it is on the same side. Remember, on the same side of the mean. Remember what I've shared, for example. Let me see if I can do this again, because I want us to understand this. So if I'm to draw this, don't mind it. So this is a mean. So let's say I'm getting the result here, and I got the result again here. So they are on the same side, and this same side, 2 of them, becomes exceed 2 standard deviation. That is 2,2S rule. Are you getting me? And it can also happen on the negative side. Okay, maybe you have it here. I'm just trying. So they are still on the same side, and they exceed 2S. Okay, 2SD or 2,2S rule. So what it means that again, once it's on the same side, are you getting me? On the negative side again, and it occurred 2 times, that is 2,2S rule. I hope that makes sense. And this can be due to what? Systematic error. Obviously, you need to do something about it straight away. Okay, because there has to be a reason why that is happening, continuously, or maybe more than once. Is that okay, guys? Okay, so 1, how many times? 2S, the standard deviation. 1, how many times? 3S, the standard deviation. 2, how many times? 2S is a standard deviation. That's just a rule. Once you understand this, every other thing we're going to explain will start making sense. Now it become a little bit challenging with what we are saying here. So this one is saying arrow 4s. So if I say 1 is how many occurrence, what then is R? Now don't be confused about this. So this arrow here I talk about 2 consecutive differ by more than 4 SD. So we already know that the 4 here is a standard deviation. So when you have 2 consecutive times, you've done it the first time, you've done it the second time, and each of the points 2 consecutive times, they exceed 4 standard deviation. That is arrow 4s rule. Do you understand me? Okay, that is arrow 4s rule. Okay, now that arrow 4s rule means that the 2 consecutive time is more than 4 standard deviation, and this can be due to what? Random error. Now if you have 4-1s rule again, so this 4-1s rule, now remember this, now things are beginning to change. So this again talk about 2 consecutive points exceed 1 SD now, okay? Because I've told you guys that 1s or 4s, whatever number you see before s is the number of the standard deviation, either as addition or reduction. Does that make sense? Okay, so but now when you see R here, it's talking about when the 2 consecutive times differ more than 4s. But when you see 4-1s rule here, it means that there is 2 consecutive points that exceed 1s, okay, and which is on the same side of the mean. Again, this one can be systematic error. I hope that makes sense. Now once you understood this, now you see when you say 10x rule, so what means that we have 2 consecutive points that fall on the same side of the mean. 2 consecutive points that fall on the same side of the mean. I hope that makes sense. Okay, so and this can be due to systematic bias. Okay, I will show you, I'm going to show us all of these examples as we progress, but I just want us to understand the rules. Especially when you go for interview, you have to explain the rules to them. I know this video is taking time. I'm taking my time to explain it because I want us to understand it. Now let's look at scenarios. Okay, let's look at scenarios. So you measure the quality control of the glucose level daily and plot on the Levey-Jennings chart. The mean of the glucose, remember what I showed us before, is 100 milligram per day. Then you have standard deviation of 5 milligram per day. So how can you be able to monitor this? What you need to do, let me now give you the secret. That's why I just did one here. So the standard deviation is 5. Okay, that's the standard deviation. Okay, the standard deviation is 5. Now, and when you run the test you are saying is giving you 2. Remember the mean here is 100. So the test you run is giving you 2. So that test of the standard deviation, okay, divided by the calibrated standard deviation, the result you are getting by the standard deviation divided by the calibrated standard deviation. For example, the test of the standard deviation you've done is 2, but the calibrated standard deviation is 5. When you say 2 divided by 5, that will give you 0.4. So if you look at this 0.4 is less than this SD, because 1 SD is 5. I hope that makes sense, guys. Okay, so that's why if you look at day 1 control is 102, because it means that it did not even add up to, it didn't add up to 1 SD. I hope you understand this. So because 1 SD is 5, it didn't add up to 1 SD. What it added, the test you did, what it gave you, your quality control gave you from your result 2, for example. So that 2 divided by the calibrated standard deviation, that will give you 0.4. So if you look at that, what it has added to this your mean is 2. So that's why you have 102. So this 102 is because what it has added to this is 0.4 milligram, which is less than 5 milligram per DL of the calibrated standard deviation. I hope that makes sense. Now, if you look at day 2, if your result is 8, okay, so that 8 divided by 5, okay, will now give you, let me see if I can check that, okay, for you guys. So if you say 8 divided by 5, that will give you 1.6. So this 8 divided by 5, don't forget, 5 is the calibrated standard deviation. The test is the SD. So what we've gotten the first time, the test we've got, the quality control we got is 2. Okay, that 2 divided by the calibrated standard deviation, which will now give us 0.4. That is why from that 0.4, we now realize, okay, if you look at it, it didn't give us even up to 1 SD. Are you getting me? Now, if you look at the second one, because it is 8, so 8 divided by 5, 8 is a test, 5 is a calibrated standard deviation. That will give you 1.6. You see it now? That is what I'm trying to show you here, okay? That will give you 1.6. So you can see that this 1.6 is less than, if you consider it, 1.6 is less than this 2 SD. Remember that for us to have 2 SD added here, this has to be 110. Do you understand me? But because it's 108, that means the test is 8. Are you getting me? It means then that it is less than 2 SD. And of course, if you do the mathematics, you are getting 1 more SD, like I've said. So these two, they are acceptable. However, on day 7, because you've gotten 112, meaning that the test has given us 12. Are you getting me? And by the time you do the mathematics, 12 divided by 5, which is the calibrated standard deviation, that will give you plus, obviously, remember this can also be on the negative side, by the way. That will give you plus 2.4. So because it's plus 2.4, that is more than 2 standard deviation. So that means it has violated 1-2S rule, and that is a warning. And because it's a warning, you don't have to repeat it. So this is how that works. So this is the Westgard rule, how we can work it out and see what that can form our decision or not. So what I want you to think, when you are saying 2 SD or 1 SD or whatever thing you think, based on where you can see your result, what you should be thinking, what is the result? Why is it going far from the mean? The farther from the mean means that you need to do something about it. Okay, we don't want the result of the quality control to be more than 2 SD, either plus or minus 2 SD, far from the mean, if that makes sense. Now let's see some examples, guys. Now, example 1, violation action. So 1-2S. Okay, don't worry about this one. So look at this, it's violate 1-2S. So this is a mean, like I've shown you. Okay, ideally we want all our results to be within minus 1 SD or plus 1 SD. That's we want it to be either at the mean or minus 1 SD or plus 1 SD. Anything like plus 2 SD or above, we don't really want it that way, but sometimes it can be warning. So if you do the quality control, remember the number of performance is 1. So this 1-2S rule, like I've told us before, means that we've done it the first time, and that first time we've done it, it exceeds 2 standard deviation. Look at it. Look at where it is. That means it exceeds 2 standard deviation. This is actually 2 standard deviation. Remember, this can also be done here, if that makes sense. Okay, it can be plus or minus. Okay, but that's by the way. So because it exceeds 2 standard deviation for the first time, that's why it's 1. Remember, if it is 2S, you have to do something about it. In fact, you have to reject it. Okay, but because it's the first time, it becomes a warning. So if one control exceeds 2 standard deviation, the action you need to take is do not reject it immediately. That's what I'm trying to say, because that's the first time it's happening. You need to check your step. Is there anything that I've not done right? Then see what you can do. Did I mix the sample properly? Is everything okay? Whatever, just do your check, and then is a warning. You need to repeat that. Hopefully that should be able to correct. I hope that makes sense. Okay, so these are the things you need to be telling them when you go for your interview. I hope that makes sense. Right, if you understood it. So look at another example, violation rule. So you have 1-3S. Again, the number of times we perform it once, but then it exceeds 3S. Obviously we'll reject it. This is very simple. So this is the mean, then this is a 3S. Remember, this can also be here. It can be also above here. It can be plus or minus. Don't worry about where it is. Okay, so once we've done a quality control, even if it is for the first time and it exceeds the minus 3S or plus 3S, we have to reject it. Remember, the mean is here. Look at how far it is from the mean. Very far from the mean. That is what you should be considering. So you can tell them during the interview that this is what 1-3S rule. That means it violated 1-3S rule, because although it is one time, 1 point analysis, however, it has exceeded minus 3SD. Remember, it can also be exceeded plus 3SD, and because of that violation of 1-3S rule, that then will reject it. So the action you take is to reject, stop testing, investigate the system, and recalibrate if needed. Okay, I hope this example help us. Okay, and these are the things you need to be telling them when you go for interview. That will help them to see that you understand. Now look at this, something similar from the first example that I gave you. You have example 3 of the violation action. So you have 2(2)S rule violation. So what does it mean? That means we've done the test 2 times. Look at it. And they are on the same spot, the same side actually. The same side. They are on the same side. So if 2 consecutive points exceed plus or minus 2 standard deviation, remember it can also be here. Are you getting me? So once they are on the same side and they exceed, they are more than plus 2 or minus 2 standard deviation, once they are on the same side, something is wrong. Okay, so what you are going to do, the action you need to take is to reject it. Why? It's likely to be a systematic error. You can investigate the potential causes like the reagent or instrument, as the case may be. Okay, what I'm teaching us here now, I've already laid the foundation, is to show you the interpretation, because that's what they will be giving you when you go for your interview. Make sure you use the word, like I'm telling you, okay, maybe it violates 2(2)S rule, something like that, okay, and say maybe the possibility, what you're going to do to reject it, the type of error is going to be, how you go to investigate, and all of that. Even when you hear the question like, when your quality control sample fail, what are you going to do? These are some of the things you can also add to that. Okay, right. Now example 4, remember what we said, arrow 4S rule violation. Now if you look at that, we say if 2 consecutive points, remember we said it before, differ by more than 4 SD, 2 consecutive points differ for more than 4 SD. Now the 2 consecutive points we are saying here, look at what has happened. See this place here, don't look at here. Okay, don't look at here. We've done the test the first time. Okay, we got this on the negative side, more than 2 SD. We did it again, we got this more than 2 SD now on the positive side. Okay, because they are, 1 point is on the positive side, 1 point is on the negative side, we call it arrow 4S rule violation. So once you see something like this, so 1 is plus standard deviation and the next is minus 2 standard deviation. So because they are on the opposite side, 1 on the positive, 1 on the minus, and 2 of them exceed plus or minus 2 standard deviation 2 consecutive times, that is arrow 4S rule violation. Obviously you have to reject it, and this can be due to random error. And again, investigate the potential causes. It could be the pipetting error or sudden, from the instrument, as the case may be. We are getting there. Now we now have we have arrow 4S rule violation. Now this is also another type of violation, violation where we now have, if 10 consecutive points are on the same side of the mean. Now you've done the quality control, everything is on the same side. We're not talking about whether it's passing or not passing. So if you look at this, they're all okay. Even here self is not that bad, okay, but we can still do something about it. But you can see, apart from here, most of them, they are within plus or minus 2 standard deviation. But the problem with this is that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, they are on the same side. It shouldn't be like that. I did Levey-Jennings chart, some can be at the mean, up, down, up, something like that. Once it's on the same side, something definitely is wrong. So when we have, if 10 consecutive points of analysis of the quality control is on the same side, we're not talking about whether it passed or didn't pass. That's not really the problem now. Once we've done it and the 10 times they are on the same side, okay, then again you can say you have to reject it, because there has to be a reason. And most of this can be due to what? Bias. Okay, this can be due to bias of shift in the system, and of course investigate the possible causes, like things like calibration, or do we change the method? Has somebody done something wrong? Somebody didn't quite follow the SOP due to bias, as the case may be. These are some of the reasons that can lead to this. Now let's look at this one. So now this is just to summarize everything. So if you look at this, all I want you to know that this one is talking about 4(1)S rule. So you've done a quality control sample 4, okay, you have 1, 2, 3, 4 on the same side, you have to reject it. Okay, you've done a quality control, you have 12S rule, so all the result on the one side for the 12 times, you have to reject it, or on the same side for the 9 times, you have to reject it, or on the same side for the 8 times, reject it. Okay, you also have 3(1)S rule. Okay, so you have 1, 2, 3. Okay, now but they are on the same side again, you have to reject it. Okay, now look at this one. This is also another one that I really want to talk to us. Now this is 7T rule. Okay, violation 1, 2, 3, 4, 5, 6, 7. Look at the way it is on the opposite direction. Look at it. So once you see it like this is a violation, obviously you have to reject it. And of course, you see these 2 of 3S rule again violation. So you have this as well. So you've done this. Remember, this is the first one. You said, okay, it's a warning. You did the second one. It looked like it has passed. You did the third one. It has gone up again. So this is 2 of 3 2S rule. And of course, it's also a violation. You've got to reject it because there has to be a reason why this keep coming up here. Now you have 6 times rule as well. So you have 1, 2, 3, 4, 5, 6 on the same side. Again, you have to reject it. All of this method I've given to you is something you have to reject throughout and investigate the potential causes. I hope that makes sense. Yeah. All right. Thank you very much for listening. I don't know if you have got any question. Please feel free to put it on the comment section. Let me know what you think. I know that this video has taken time, but I would really tell you to take your time to listen to it and make sure you understood it correctly. That will really help you in the interpretation of Levey-Jennings chart. And of course, when you are presented any Levey-Jennings chart or to interpret during your interview, you won't just say it passed or failed. You can be able to tell them the rules that it has violated, or as the case may be. So you can mention 1S2 standard deviation or 2S2 standard deviation, so you can be able to mention that, even if you may not be able to remember, like maybe something like arrow 4S rule or 13S rule. Maybe you may not be able to remember that correctly, but if you can learn it like I've shown you, that will be fine. But let's say you are not able to mention the particular rule as per the name, like 12S rule. You can actually explain it, and that way they can be able to understand. Remember, the essence of this Levey-Jennings chart and Westgard rule is to see that all the processes in place, they are functioning the way they're supposed to function. That way, it can help us to detect the possibility of errors, either systematic errors or random errors on time. We can detect it early, okay? And that means that with the help of the Westgard rule, we are able to either reject the quality control or be able to accept the quality control, or be able to see it as a warning and investigate it. That is why it's important. So I wouldn't worry so much if you're unable to memorize all the rules of violation and all of that. But make sure you understand what it is. And remember, when your quality control sample failed, what are you going to do? In answering this question, you can also link it to why, when quality control sample failed, we should investigate the possible cause, whether it's a systematic error or random error. I know that this video has taken time, but hopefully that will be beneficial. Thank you very much. Let me know what you think about the video, and I wish you guys all the best till I come back away again. Bye bye.